So how do we know that in a normal distribution or in a symmetric distribution, a unimodal symmetric distribution? That's what we don't really know it's a normal distribution yet. That won't come till chapter 7 when we formally, or maybe 6 when we start formally studying that. But right, for now, it's safe to say if I've got most of the data is grouped up in the middle, and you get two tails, and it's symmetric on both sides. I mean, this is kind of like a chapter 3. I'm getting into chapter 3 here. We can say that most of the data is collected in the middle. In fact, if you look at that empirical rule on what page is it? I don't remember. I'm not going to go look it up right now, but it is in chapter. I don't want that. I want to do this. I want to do annotate. I want to write here. We know that 95% of the normal distribution will fall within 2 standard deviations of the mean. And the easy way to calculate that is use z-scores. You remember, when we do a z-score, we're going to take the measure, the number we're interested in, minus the mean, divided by the standard deviation for that distribution. Okay, so in this model, this is about z-scores. They don't actually have a mean and standard deviation. This is like a graph of z-scores, and we know that. So there's only a 5% chance. In fact, if you look at this applet, you're going to use this applet in chapter 6. There's less than a 5% chance of an individual falling more than 2 standard deviations above, or 2 standard deviations below the means. See the means here in the middle. The zeros there is because if the number we're looking for is the mean minus the mean, now we're getting math, divided by the standard deviation. Well, isn't that just 0 divided by whatever the standard deviation is? And that's 0 divided by anything is 0. So that's why the middle where the mean is z-score of 0. So let's do some math instead of talk about that. Let's do some applications to talk about theory. But just know that if we're more than 2 standard deviations away from the mean, we can say this isn't likely to happen just due to chance. So it's unusual. Some people get hung up with, well, what's usual? Well, it's typically very possible to fall in this range. So that's not unexpected. I like the word unexpected rather than unusual. But it's whatever. So let's go look at a couple of problems in the book here. Let's see. I'm going to clear my writing. How do I do that? Whoops, annotate. Sorry about this here. So now in my text in the book, except you need the pointer. It's very early in the morning. I need coffee. Here's this one. Let's look at, I haven't done number 11 yet this semester. Let's try that one. Number 9, I post in the discussion forums. You can go take a look at that. Go look up the answers in the back of the book. And notice number 11 is an asterisk problem. So that means you have the worked out answers available. If you bought the PDF or bought a paper copy of the book, you have the answers in the back. I also have them in that week 0, or maybe it's a course resource area in Canvas. So let's see, we got Tom Brady's wife. I don't know, Giselle, is that how you say her name? She's 71 inches tall, and is she unusual with respect to the top models? Well, let's see, we go up here to this table, and here's the mean for the top models, and here's the standard deviation. So let's see, she is 71 inches tall, minus 70.7. So there's the 71, the number we're interested, minus the mean for that distribution, divided by 2.2. And that's going to be what? Let's see. 71 minus 0.7 is 70.7, and I believe 0.3. 0.3 divided by 2.2 is going to be a pretty small number. It's going to be above the mean, because I know it's positive. I could see it's above the mean because 71 is bigger than 2.2. But let's get an actual value. So that tells me that she is about 0.14 standard deviations above the mean. Well, that's a whole lot less than 2. She'll really, what it kind of looks like is, here's the distribution, here's the mean of what was 70, and she's falling just about here. So certainly within 2 standard deviations. Now, you probably have seen some people writing in, well, let's see, what is 2 standard deviations? So if I take 2 times 2.2, That's 4.4. And if I add that to 70, I get 74.4. And if I subtract that from 70, I get what? 55.6 or 65.6. So any model that is less than 75.6 is considered unusually short, and any model taller than 74.4 is considered unusually large because tall, because that they're more than 2 standard deviations away from the mean. Okay, so that's how that works. We found out that Giselle was not 0.4, was not unusually tall for the models. Let's see how she compares for the all women, because I think that's what the next question is, right? So let's see, she's 71 inches tall, but for all US women, the average height's only 64. So minus 64 divided by 2.8. So 71 minus 64 is 7. I should have been able to do that in my head, sorry. 7 divided by 2.8. Well, I already see this is going to be bigger than 2, isn't it? So that's a z-score 2.5. That means she's 2.5 standard deviations above the mean for all women. So she's unusually tall compared to the rest of the population, of the U.S. population. So the subgroup model, she's not, pretty close to pretty much average. So U.S. women, compared to the rest of the U.S. women, she is very tall. And at times she's unusually tall compared to them. Okay, so that's how you'd use z-scores to determine unusual or not. Yeah, so I guess I'll stop here and not make this video any longer. Give a yell if you need more help.